All right, so we've been doing hypothesis tests with proportions. And 10.3 turns that around and says, okay, let's do them with averages, with means. So I made up these tables just to help you compare and contrast. Right here, this should say population mean. But notice, how do you get the standard deviation of each? Because you use those in these tests. Proportion, mean, what are you measuring? P hat, X bar. Lays out how you do the hypotheses, whether it's a one-sided or two-sided for both of those. That, again, should say population mean. For proportions, we're using z-scores. For averages, we're using t-scores. When it asks you for a test statistic, that's what it's talking about. Either z sub 0 or t sub 0. Notice the formulas are different, but they're in your formula pages. Here's how you make your decision. Notice something. The conditions are the same, except when you're talking about, is my sample normal enough? Is that sampling distribution normal enough? For proportions, you do the NP times 1 minus P greater than 10, greater than or equal to 10. Not so for averages. There's two ways for averages to work. Number one, if your sample's bigger than or equal to 30, that's almost always going to be the case. Or if you've got a smaller sample, what's the population normal? Either one of those will work. Okay, first problem. Mr. Burns has these fried chicken stores, and he puts an ATM machine in all of them. We know that just for ATM machines in general, the average amount withdrawn is $67. So Burns gets Smithers to do a random sample of 40 just to see, is that average about the same for our stores? And Smithers gets an average amount of $73 from that sample. Standard deviation for the sample is $12.50. So we're wanting to test at the alpha equals 1/100th level. Do people really, in general, withdraw more money from the Cluck Buck machines? Now, for the sample, they did. But we can't just generalize about that. We need to do a hypothesis test. So the first thing we do is our hypotheses. Well, the null is always, this is no different from everybody else. This is the status quo. Nothing's changed. And so our null hypothesis is that the average of these Cluck Buck machines is no different from ATMs in general. I should have put H1 there. Our alternative is no. People withdraw more money from these machines than just your average ATM. And notice we're talking about mu here. We're not talking about P, because these are averages that we're looking at. All right, next thing we do, we look at the conditions. Was our sample random? Yeah, the problem says it was. Distribution normal enough? Yeah, our sample size was at least 30. Were the ATM machines that we're looking at here in the fried chicken stores, were they independent of each other? Yeah. 40 of them is less than 5% of the ones in all his stores. So we're good. So we've got our hypotheses set up. We've got our conditions checked. Now we need to do our test statistic. And so I'm going to plug in the values that we got. Notice the 73 is what we got from our sample. The 67 is our null hypothesis. Here's what I got. Go ahead and make it 3 decimal places because the table you're going to be using is 3 decimal places. All right, so far so good. Now we need our critical value. How do we do that? Now we're not using z-scores now. We're using t-values and t-scores. T sub O. So we go to that table of t-values. I just put part of the table in there because I couldn't get the whole thing. So we got 40 in the sample. How many degrees of freedom are we talking about? 39. So I'm going to come right here. And now then alpha is 1% on this. One-sided test. So keeping my finger there on the 39, and then I'm looking for 0.01 up here on top. And where those two things meet, that's 2.426. That's where I got that number. That's where degrees of freedom and alpha intersect. All right, so we're here. Got our critical value of that. And then I'm going to place those two numbers, my T sub 0 and my T alpha, over here. There's T alpha, there's T sub 0. And if you know what you're looking at here, you can tell me at this point right here whether you're going to reject the null or not. Now notice T alpha marks that dividing line, that if we cross that into the blue territory, we're going to reject the null. Well, T0 did. So I know at this point right here, just from my drawing, I'm going to reject the null. I highly suggest just making a goofy little drawing like this. It's a right tail test. T0 is bigger than T alpha. If it were a left tail test, we'd be looking for T0 being less than T alpha. So make sure you got that in your head. Another way of looking at it is, well, which one's more extreme? Which one goes further out away from the middle? Let's make a decision. What we just did, really, all I'm going to do here is just write out what we just looked at in the drawing. T0 is more extreme. It's bigger than T alpha. So I reject the null. Pretty easy call. Very similar to the z-scores, the z sub 0 and z alpha that we just got through working with proportions. All that's left is a conclusion. Here's what you do. You mention the level of significance, alpha. You mention whether you're going to reject the null or not. And then give me some information about what the null was saying. That's going to work for our purposes. Now, again, what's the population we're talking about? It's not ATMs in general. It's just these machines, the Cluckbuck ATMs. Question about that one? Let's look at another one then. That's where I got that. Now then, here is the p-value approach. What's the only thing really different here? It's this decision part. The conclusion should still be the same, whether you're doing classical or p-value approach. So look what I did. I put my T sub O here. I'm looking at the degrees of freedom, 39. This value, 3.036, is between 2.976 and 3.313. Make sure you see that in your formula pages. This is as exact as we have to get. All right, so my test statistic here is between these two numbers. So you come up to the tops of the columns and look what's up here. There's our p-value. Our p-value is between 0.001 and 0.0025. That's a probability now. It's between 1/1000th and 25 10,000ths. Make sense? So our probability is between 0.001 and 0.0025. Is that less than alpha? Yeah. Yeah, even the left-hand end of that interval is less than alpha. So that right there would tell us, okay, our p-value is like this. And that's not a bad way to write it. We know the probability of landing out there where we did, if the null is true, is between those two values. But that whole range is less than alpha. This is like horseshoes. You don't have to know the exact p-value to know that we're going to reject the null. If you want to see how to do it on a calculator where you get it exact, I'll sure show you, but you don't need to for this quiz. It can get confusing because there's so many functions in the calculator dealing with this that's really easy to get the wrong one. All right, so we know we're going to reject the null. Whether you do the classical approach or the p-value approach, you ought to be getting the same result, right? Either reject the null or not. Those are really your only two choices. Either this defendant is guilty or she's not. It's not like, well, kinda. Question about that one? Notice how similar it is to the proportion ones. Same logic, same setup. The formulas are a little different. And using this table is different from the z-score one. Let's do another one then. And again, I should have written the H1 there. So we know Burns owns thousands of cars. Homer takes a sample of 50. Burns wants his fleet to average at least 26 miles per gallon. Homer's sample didn't turn out like that. It missed by a little. It was 25.02 miles per gallon with the standard deviation that's shown there. So Homer's feeling bad because he thinks, well, I've failed as a manager of this, and we're going to do a hypothesis test to see if he really has or hasn't. I know this sample was smaller, but that doesn't mean overall that the cars are failing this. All right, so our null is, yeah, these cars are making it to 26 miles per gallon. We are for a second assuming that's true, and if it is, do our tests bear it out? So our alternative is, no, they're really getting less than 26 miles per gallon. Maybe this sample was the good ones. Maybe the fleet as an average is getting way less than 26 miles per gallon. We don't know. Notice this is a left tail test because it's less than. So what do? Condition time again. Random? Yeah, the problem tells us it is. Is our distribution normal enough? Yeah, our sample size is at least 30. And we know that these cars that were sampled are independent of each other because, well, we're assuming that because they represent less than 5% of all the ones that Burns owns. So we met our three conditions. Now, what if you didn't meet one of those conditions? You would say, you'd write out, does not meet this condition. If it's part of a problem that they want you to work the whole thing, then say, yeah, I'll go ahead and work the whole thing, but my result might not be valid. Yes, ma'am. If you think way, way back in chapter 8, I think, we decided a sampling distribution was normal for means if the sample size was at least 30. That's where it's coming from. I'm glad you asked. It's sort of a magic number. We did a thing in class where it showed no matter how skewed the population was, if the sample size reaches about 30, the sampling distribution part's pretty normal. So I'm going to plug in my values. The 26 is our null hypothesis. The other values were given in the problem. So I'm getting that. So in your formula pages, what's alpha on this one? 0.05? In your formula pages, see if you can find out what the critical value is. Now this is a left tail test. How many degrees of freedom do I have? Here's a problem. Once we get to 40, they don't break it down by ones. So got 50 in my sample, so that's what I'm going to use. That's the closest that we got. All right, so I'm looking at the 50 line, and alpha here is 0.05, right? So where do they meet? 1.676 right here. But y'all, that's for a right tail. Now remember, this t-distribution is symmetric. So all I'm going to do is stick a negative in front of that. So I've got negative 1.676. So that's what I got in the table. But that's positive, and I'm talking about a left tail test. So I'm going to change it to that. Again, that matches my drawing. That's our critical value. If I cross over that spot, then I'm going to reject the null. So I'll mark it right there. And then our t sub 0 is here. Now looking at that drawing, what decision would you make? Would you reject the null or not? Not, because we didn't cross over this threshold to be out in the blue. In this case, notice our t sub 0 is less than t alpha. If we're talking about the negative side, that means you don't reject. If you look in that little table I gave you, it'll show you that. Decision time. Well, since t0 didn't make it all the way out to t alpha, I'm not going to reject the null. It has to cross that line in the sand that t alpha represents. Conclusion time. Say something about alpha, say whether you're going to reject the null or not, and then it kind of give somebody some information about what the null was talking about. Long sentence. As long as you get your information in there, it doesn't have to be like mine. But that's not a bad one. Let's look at another one. Last example. Oh, let's do the p-value approach. Forgot about that. Now look what I'm doing. There's my t0, my test statistic, and notice at 50 degrees of freedom, it's between 1.299 and 1.676. Okay, what does that mean? That means the p-value is between these two numbers at the top of those columns. So notice something. The lower value of that interval is 0.05. Isn't that what alpha was? Yeah, but notice our t score here doesn't get all the way out that far. So we know we're somewhere in between 0.05 and 0.10. Not equaling either one of those. Which means what? Our test statistic is bigger than alpha. Our p-value is bigger than alpha. So we don't reject the null. Just to make sure, if they give you alpha and you find a p-value, if the p-value is less than alpha, you reject. If it's equal to or greater than alpha, you don't reject. If it's exactly equal to it, you're right on the line. That's a tough call. So what do we say? we say, here's the interval where our p-value, our probability of being out as far as we hit, assuming the null is true, that probability is between 5% and 10%. That's bigger than alpha, which means we don't reject. Now, that's exactly the same answer we got when we did the classical approach. That's a good thing. They should match. A p-value just gives you more detail. Classical approach, p-value approach, we've seen two problems based on those. One more, last example. So what do we got here? 5 years ago, the average amount of time that workers spent goofing off was 2.1 hours. All right, Bart wants to know, has that changed in the intervening 5 years? So he gets a sample of 15 workers and gets their goof off time. And we're going to use alpha at 0.01 as the level of significance. Notice on this is a two-sided test. He wants to know, has it changed? Either has it gone down, has it gone up? Two-sided. And so your alternative hypothesis has that not equal to sign on it. Could be higher or lower. That's what we're testing for. All right. The null is, no, it hadn't changed at all. It's still 2.1. Now, what's 2.1? That mu represents what population? 5 years ago people or today's people? Today's people. We know what it was 5 years ago. We don't have to estimate that. These things are today's people. What's today's average? Okay, if you'll put these values into your calculator. Anybody not through getting those values in? So now you go to what? Stat, calc, one-var stats. And that's going to give you the average and the standard deviation, which is what we really need. The problem did not give those to us. Some problems will, some will ask you to enter this information. So here's what I got, the 3 decimal places. And round your standard deviations off to 4. It makes your results a lot more accurate. If you're not getting that, let me know. We good? Okay, so how are we going to use them? Well, we're going to look at our conditions again. And a good question came up, is 15 big enough for a sample? It is if what? The population's normal. And this problem told us the population was normal. So random, yeah, the problem said so. Independent workers, yeah. 15 is less than 5% of all the workers that Burns has. Start filling in our formula. Those values represent X bar and the null hypothesis. That's how I really want to say it. Plug in these. And here's what I'm getting. That's T sub 0. That's your test statistic. Now looking at that, our sample ended up on the right-hand side of our graph. It could have ended up on the left-hand side, but this sample didn't. It ended up on the right-hand side. What's our critical value? I'm getting that. Now what's alpha? 0.01. Yeah, 2.977. How did I get that? Let's go see. All right, take a look. We got 14 degrees of freedom because there were 15 in the sample. What is alpha? 0.01, right? So I get on this 14 degrees of freedom line. Why am I looking there? I'm looking under the 0.005. Why? Good. It's two-sided. It's two-tailed. Alpha is 0.01, but I got to divide it between two equal tails. Watch out for these. It's going to work the same way in the proportion ones too. So two-sided test, I know what alpha is, but I got to split it. So I'm looking under the 0.005 column, and that's where I'm getting the 2.977. Watch out for two-tailed tests. So let's go back. So there's my T alpha, and notice I put divided by 2, because that's really what it is. There's my line in the sand. Did we cross it? Nope. Our T0, our test statistic, didn't make it out far enough to be considered statistically significant. Meaning it didn't cross this line. So on two-sided tests, what do you have to watch out for? You better divide alpha by 2. Okay, decision time. We've already made it, basically. We know that our test statistic didn't make it out as far as our critical value. We can't reject the null. So conclusion time. Again, mention what alpha is. Mention whether you're rejecting the null or not. And then if somebody's just reading this, let them know what the null was at least talking about. In other words, at that level of significance, we don't have enough evidence to say that anything's changed from 5 years ago. Now, maybe it has, but we don't have enough evidence to prove that. Again, just because the jury found somebody not guilty doesn't mean they're innocent. They still might have done whatever it is they were accused of. There just wasn't enough evidence to prove it. It's really logical when you get right down to it. Okay, we're not rejecting that null. What was the null? That today's workers are goofing off an average of 2.1 hours every shift. Well, let's do the p-value approach. I'm putting my test statistic where it goes. For 14 degrees of freedom, it's in between 1.761 and 2.145. Okay, so I know it's coming up the middle there. I look at the top of those columns, and I'm getting that. So the probability of results as extreme as we got, assuming the null is true, is between those two values. I got a question for you. What if alpha was 0.05 instead of 0.01? In this problem, it's 0.01, but what if it was 0.05? Would you reject? The answer is yes, because our value is in between 0.025 and 0.05. Now notice it's not equal to 0.05, which means it's smaller than 0.05. Would you reject? This is a two-sided test. We just got a one-sided answer. What do I have to do to that probability? I got to multiply those endpoints by 2. See, I've got this situation right here. So I've got to take this interval and multiply those two endpoints by 2. There's our real p-value. For a two-sided test, not only do you have to divide alpha by 2, you've got to multiply the p-value by 2. And that's whether it's an average or a proportion. So watch out for that. Two-sided tests are just waiting for you. Big briar patch. When I did it on a calculator, I think it came out to be 0.07 something, but it's in between 0.05 and 0. So the last thing I put on your notes is, well, next to the last thing. Same conclusion we got before, as it should be. the p-value represented by the blue stuff is bigger than 0.05. And I put 0.05, that should be 0.01, shouldn't it? Still bigger. Don't reject. Okay, this confidence interval. If alpha is 0.01, what does that leave? 0.99. And for a two-sided test, the confidence interval and the hypothesis test are really just reinforcing each other. For my 99% confidence interval here, represented by the green lines, I'm saying what? I'm 99% confident that that true average for the population that we're talking about is in between those two values, 2.048 and 2.378. I'm 99% confident. That's pretty confident. Well, where did our test statistic end up? There's our null. It puts the null right in that interval. So if I'm saying on one hand, I'm 99% sure that's in between here and here, and it ends up being there in our sample, I sure can't reject the null. That wouldn't make any sense. If the null, on the other hand, was down here below 2.048 or above 2.378, then I could go, well, yeah, at the 1% level, I'm going to reject it. So for two-sided tests, realize you can get the same results, just not a p-value, but you could reject or not based on that. That's it for me. Next week, we'll look at chapter 4 a bit.